السلام عليكم صبايا وشباب، كيف الحال؟ I will go through this example again that we end up our last record with because it's an important example to understand what is going on. Again, it's about that reading of a scale inside the elevator and how it will be different than reading the scale on the normal ground without the elevator, and how it will be different if the escalator or the elevator is moving with an acceleration a, or if it's moving with a constant speed with a is equal to 0. So again, we are in front of two situations. We have a scale, it's inside the elevator, and that elevator is going through two situations. One of them, the elevator is going down with a constant acceleration a. The other, which is part B, the elevator is going down with a constant speed of 2 meters per second. Constant speed means an acceleration of 0. So one with normal constant acceleration, the other is with acceleration is equal to 0. And we want to see the reading of the scale in each one of them. For your information, if you see what is the reading in the scale while you are moving inside or while you are in a moving elevator, it will basically read the reaction force of the surface on the object, and this what the scale will read. So it will read Fn. Mama. So it will read Fn. So in other words, we will calculate Fn in both cases. One when we have acceleration, and the other when acceleration is equal to 0. In both cases, we are applying Newton's second law. So for the first one, summation of the forces acting on the object, as I mentioned to you, it's either you say it's Fn, which is whatever is up, minus mg, but you have to pay attention that if you say it's up minus down, which is Fn minus mg, then you have here also not to forget that acceleration is down. So it is not just ma, it is minus ma. So it will be m times minus 0.2 g, which is the value of the acceleration. Or you will follow something that we are following now, that whatever is with the direction of motion, it's positive, and this is our dimension of motion. So whatever with the direction of motion is positive, and whatever is against the direction of motion is negative. Our motion is downward, so mg minus Fn, which is against the direction of motion, is equal ma, which is positive. Definitely it's our direction of motion. And both of them, both situations will give you the same answer. So suppose we agree on the sign notation and we got it correctly. So what is the value of Fn? Fn from this equation is mg. We bring Fn to this place. So this is Fn, and then the m.2 g will come to the other direction, right? This is math. It's up to you how you do it. So Fn is equal mg minus 0.2 mg. And if you see, the example prefer to keep it as mg because it's common. So he want to show you, you know how he got the 0.8 here? It is 1, basically this is 1, right? So it is 1 minus 0.2 is equal 0.8. So it's 1 minus 0.2 is 0.8 mg. And still, This is what I always encourage my students. Do not plug in the numbers. Don't say here it's 10 and 9.8. Keep it as mg. Basically, this is indication. What is mg? mg is the force of gravity, Fg. So the normal force usually, or in some cases, is equal to the force of gravity if we are on simple horizontal surface, right? But here, this is a very good example to show you that for normal force is not exactly equal to the force of gravity. Instead, it is less. It's equal 0.8 of the force of gravity. You know that when you multiply anything with a fraction, it will be less, a fraction which is less than 1. It will be basically this one is less than this one, right? So you can see that Fn, which is the reading of the scale, will read only 0.8 of the actual weight of the object. So basically it looks like an apparent weight loss, right? So if you get the scale and you go to the elevator, and the elevator is going down with a constant speed, with a constant acceleration, and you step on the scale, for example, let's say that your actual weight is 65 kg. The reading on the scale inside a moving down elevator will be a little bit less than that, okay? Now, so I hope I make this clear to you guys. And one more thing we have to make it clear, that if your weight is 65 kg, basically the weight is 640 Newton. It's 640 Newton, right? Because you know it is mg, the weight. Good. Now, what if the object or the elevator is moving down with a constant speed of 2 meters per second? I really don't care for the value of the speed. I do care that it's constant. If it's constant, immediately I will understand that acceleration is equal to 0. So the same equation will apply, but the right side of the equation will be equal to 0, we will go back to our normal kind of example, that an object is on the horizontal surface. mg minus fn is equal to 0. So mg is equal fn. So fn will be exactly equal to mg. So it's exactly, the reading of the scale will be exactly like the reading of the scale on a normal ground or floor, as if the elevator is not moving. It means the reading of the scale on a normal stable ground will be exactly like the reading of the scale inside an elevator, only under one condition: if acceleration of that elevator is equal to 0. All right? So these are the two situations. Thank you, and I will see you in another record explaining section 4.7. But I thought that this example of a scale inside an elevator and different kind of direction of motion, once with a normal acceleration and the other with a 0 acceleration, but both of them are moving downward, that worth a small short clip. And I hope that I made it clear. Okay guys, see you in the next record.